So in this video we are going to discuss about surface impedance. Surface impedance, the definition is the ratio of tangential component of electric field intensity at the surface of a conductor to the linear current density is called as surface impedance. Let me repeat it. The ratio of tangential component of electric field intensity at the surface of a conductor to the linear current density is called surface impedance. It is given by the formula Zs is equal to E tan divided by Js. That means tangential component of electric field intensity divided by surface current density. Now let us derive the value of this Zs. To derive the value of Zs, we are considering a flat conductor like this. This is a flat conductor lying in Z axis. Now what happens is, when this is a flat conductor lying at Z axis like this, so let us consider this pen as the conductor. This is the conductor lying in Z axis. Now what happens is the current density will be distributed in perpendicular axis of it, that is in Y axis. Just see the direction of my hand. So this is going to be the thickness. So current density will be in the Y axis. So let me repeat it. You consider this as a conductor lying in Z axis. So what happens is the current density will be flowing in Y axis. So that is what given here. That is, consider a flat plate conductor with the current density Js ampere per meter. The current density of this conductor is Js ampere per meter. So because of this, what happens is the current density will be distributed in Y direction, that is perpendicular direction to the surface of the conductor, which is given by J is equal to J0 e power minus gamma Y, where gamma is the propagation constant. Gamma is the propagation constant and J0 is the current density at the surface. So from this equation we can plot the relation between that is the distribution of the current density. So distribution of current density can be plotted like this, which is an exponentially decreasing curve. So this point is J0. J0 is at the surface what is the current density. When the thickness of the conductor is higher than the depth of penetration, when the thickness is higher than the depth of penetration, there will not be any reflection coming back. When thickness increases, the reflection won't be coming back to the surface. So it will try to go inside and there won't be that much reflection available back to the surface. So based on this we can derive the linear current density. Linear current density is Js is equal to integral 0 to infinity J into dy. Instead of J we are substituting it J0. The lower limit is 0 and the upper limit of Y axis is infinity. So J0 e power minus gamma Y dy. We have to differentiate with respect to dy. So differentiating with respect to dy, Js is equal to minus e power minus gamma Y by gamma with the limits 0 to infinity. So after integration we have to substitute the limits. By substituting the limits we get the surface current density Js is equal to J0 by gamma. In the fourth module we have discussed about current density and two types of it, that is displacement current density and conduction current density. Here we are considering the conduction current density. From conduction current density equation we are writing down J0 is equal to sigma into E tangential. Take it as equation number 3, where sigma is the conductivity of the medium. Now substituting the value of 3 in 2, we get Js is equal to sigma E tan divided by gamma. Take it as equation number 4. The general formula for surface impedance is E tangential by Js. So Js we have find out the value. Js is equal to sigma E tan by gamma. So substituting it we get gamma by sigma. That is, the surface impedance is equal to gamma by sigma. Take it as equation number 5. So we have derived the expression for surface impedance Zs, which is equal to the ratio of propagation constant by conductivity of a medium. From this Zs we can calculate the value of Rs, the surface resistance and the surface reactance. To derive it, let us consider the propagation constant for the conducting medium, which is gamma. For a good conducting medium, gamma is equal to approximately equal to root of j omega mu into sigma. This we have derived in module number 5. Take it as equation number 6. So Zs, we know Zs is equal to gamma by sigma. So instead of gamma, we are writing down this expression divided by sigma. So whole root means what happens is sigma will become sigma square. So this becomes the equation. So from this sigma will get cancelled. So we get Zs is equal to root of j w mu by sigma, which is approximately equal to neta. Neta is the intrinsic impedance. So when the thickness of the conductor is greater than del, which is called as depth of penetration or skin depth, the surface impedance is almost equal to intrinsic impedance. So what we can conclude is, when the thickness of the conductor is higher than the skin depth or the depth of penetration, the surface impedance is equal to intrinsic impedance. So intrinsic impedance neta is equal to Zs, which is equal to this particular formula. Instead of j, we can write it as angle of 45 degree. The reason for this conversion is we have Zs is equal to Rs plus j into xs. So that can be written in this particular form. So with these two functions, we can find out what is the value of Rs and what is the value of xs. So to find out the value of Rx and xs, the equation can be written as Rs plus j into xs is equal to root of w mu by 2 sigma plus j into root of w mu by 2 sigma. And equating the real and imaginary components, the real component will give surface resistance Rs, imaginary component will give surface reactance Xs. So surface resistance Rx is equal to root of omega mu by 2 sigma, and surface reactance is root of omega mu by 2 sigma. Based on these two expressions, we get the skin depth delta is equal to root of 2 by omega mu sigma. So from equation number 10 and 12, we can state that the surface resistance is inversely proportional to conductivity and also skin depth. So as long as skin depth is more, the surface resistance will be less, or we can put it in another terms, when conductivity and skin depth are less, the resistance will be more, or when resistance is more, the conductivity and skin depth will be less, right? So the surface resistance of a flat conductor at any frequency, you have to mark the term any frequency, it is equal to the DC resistance of the conductor with the thickness del. This is the reason for which when we calculate RAC, we multiply it by 1.6 into RDC. See, this 1.6 is called as skin effect factor. This is about surface impedance and surface resistance. So to summarize, surface impedance is the ratio between tangential component of E bar and the conductivity of the medium. So in other terms, when the thickness is very greater than the skin depth, then surface impedance is approximately equal to intrinsic impedance of the conductor. From this we can find out what is the value of surface resistance. Surface resistance becomes inversely proportional to conductivity and depth of penetration. So with this we have learned what is surface impedance and surface resistance of a conductor.